Now, as we see that in physical situation, I have given you one instances, I'll cite you a few more instances in which there would be requirement of taking, here we are taking the component of area, somewhere else we'll be taking the component of displacement or component of force. We have to take component of one thing or the other. So simply straightforward multiplication will not work. As you can observe here, straightforward multiplication of energy per unit area and area will not work here. We have to take the orientation also into account, and the orientation is taken into account by considering the angle between the area and energy per unit area here. And that is mathematically put in form of vector, and we have defined the direction of area vector as in the perpendicular to the surface of the area. If the area is oriented like this, then the direction is perpendicular to the surface of area vector. And energy per unit area, I told you, is coming vertically downward. And from here we also saw that the orientation with the horizontal actually is the angle between the two vectors. So now we don't have to bother about the orientation of the surface. We have to consider the area angle between the vectors, which we are more familiar with. So what we have to do now, if you have to calculate the energy coming on the surface, you have to know the area vector, you have to know the energy per unit area vector, and you just have to do the dot product between them. The dot product is just a matter of convenience. We have defined, actually we know that it is Ea cos theta. So we have defined Ea cos theta as E vector dot A vector to bring them into the vector algebra. Because we want to deal with vectors, it actually helps. As we move forward, you would observe that this thing helps a lot. We want to somehow incorporate vector. So we have defined E vector dot A vector because we know the light energy per unit area quantity is actually a vector. It has a particular direction, and forcefully we have defined area as a vector because again it's going to help. So these are vectors. Now somehow we are dealing with vectors. Now we have defined a kind of multiplication of vector in which A vector dot B vector is equal to A into B into cos theta. In this case, E vector dot A vector is E into A cos theta. So if now you have a formula for total energy being radiated on a surface. That formula is E vector dot A vector. So E vector dot A vector is Ea cos theta. If you know the angle between the energy vector and the area vector, and you know the magnitude of energy per unit area vector and the area vector, then you can find the total energy. Okay, so this actually clears one thing, that's total energy falling on a surface will not be simply energy per unit area into area, because that is wrong, and we have corrected that by dot product instead of simple multiplication. So this dot product is also called as a scalar product because we have not attached any direction with the product. Even though on the left hand side we have vectors, but the right hand side would be a number. There will be no direction attached to that number. So it's a scalar thing. So it's a scalar product, and since the symbol is dot, it is also called as dot product. Okay, let's talk a little bit more on this. Now in this, we were changing the area or orientation of area, but suppose there's a surface and you're falling a light, again the same beam of light, and this is the length corresponding to the area which is being illuminated by the light. Instead of changing the area, if you change the orientation of the beam, the same beam, this is the length corresponding to the area which is being illuminated, which is larger. Obviously, if you make the light beam oblique, then a larger surface will be illuminated. But the point is, will the total energy falling on the surface will change? No, it will not change. So I'm just going to show you that if we use a general formula of E vector dot A vector, this is going to give us the total energy irrespective whether you are changing the orientation of the surface or you are changing the orientation of the light beam which is falling on the surface. It's not going to make any difference because the E dot A is E into A into cos theta. Now theta, this magnitude is going to remain the same, but this theta, this angle would change, and this angle would be will not depend on whether you have changed the surface orientation or you have changed the beam orientation. This is the net angle which is between the surface and the beam. In this case, if from extending the idea of the previous discussion, this is the area actually through which the light would come, and then it will spread out. So whatever energy crosses this area, the same energy will be fallen on the surface irrespective of what is the area which is being, what is the surface area which is being illuminated. Even though that is larger, the more energy is not going to come. So for calculating the total energy, what we have to do is we have to calculate this surface, the length corresponding to the surface area corresponding to this length. What we have to do, we have to take the component of this area, the total area which is being illuminated on the surface. If you know this angle, if you know this angle, then A cos theta will be the area through which beam of light is coming before it is getting spread out. So this is the area through which the beam of light is coming before it is getting spread out. So whatever area energy is crossing this area is that same amount of energy is going to spread out, and the areas illuminated will become larger, but the total energy will remain the same. So if we have to calculate the energy falling on the surface, what we have to do again is just this area into energy per unit area. Okay? Now, we have been given that this is area A is being illuminated, and we have been given that energy E, energy per unit area is E. Now we have been asked what is the total energy. Now again we can't do simply A into E, because that would be wrong. Area A is the total illuminated area, but that is not perpendicular to the beam of light. We have to calculate the area A which is perpendicular to the beam of light. We are interested in this area given this area. Now, if you do the dot product, you will get this area. How? See. This is the beam of light. This area is given. Now, we are interested in calculating this area. If somehow we get this angle theta, then this area, the required area, is given area cos theta. Components. Now, you should be very fast and efficient in calculating this. This is A cos theta. Now, vector. This is the area illuminated. The area vector is perpendicular to the surface, and the energy per unit area vector is like this. This angle, if the angle between the two vectors is theta, then this angle is also going to be theta. That would come from simple geometry. If you just draw the vectors again here, from here you can figure out if this is theta, then this angle is also theta. So what you are looking for is E cos theta, and if you do simply E vector dot A vector, you will get EA cos theta. If you look at the angle between the vectors, that is going to be the angle you are looking for calculating the area perpendicular to the propagation of light. Fine. So you don't have to look actually the orientation between the beam and the area if you know the angle between the area vector and E vector. So in most of the cases you'll be given area vector and E vector instead of the angle or inclination of the area surface. So because we are dealing with vectors, that's why we have defined area vector like this to be perpendicular to the surface, so that this angle and this angle actually becomes the same. Fine. So this is the demand of the physical situation to define something like this, because simple multiplication, the arithmetic that we have studied, one quantity into another quantity, that is not going to work in a situation like this. So if we define a multiplication which is E into A or A into B into cos theta. I'll cite you one more instance in which such kind of thing would be demanded. Now, the thing is, here we are studying scalar product or dot product. We are not studying the total energy falling on a surface, or the thing that I'm going to study now. I'm going to teach you now. So don't panic if it is falling a little bit hard on your ears and brain, because whatever is expected out of you to learn from here would be very simple, which I'll actually boil down in few things. after I set the context from this one more example. Suppose there's a surface like this and you are pulling a block with a string, applying force F, and the angle between the string and the horizontal is theta. Now work done, you must have studied the definition of work done in class 9th. Work done, what you studied is force into displacement. Now applying this force, you cause certain displacement of this block, and suppose this block moved a distance d. So work done would be force into displacement. But in this case, it won't be simply force into displacement, because again force is a vector quantity, and when you would resolve this force into horizontal and vertical component fx and fy, you would realize that fy has nothing to do with the horizontal displacement, because fy is in vertical direction and the horizontal direction is perpendicular to fy. And if you think of the f component of fy along the displacement, it would be 0. We take to find a component of a force along a direction, we do f cos theta. Theta is the angle between the force and that direction. Now if you have to find the component of fy along horizontal direction, the angle is 90 degree. So component will be fy cos 90. Cos 90 is 0. Now fy has no component along horizontal direction. So if any displacement has been caused along horizontal, then fy is not responsible for it. It is only fx. So the definition that you studied in class 9, that was applicable only if the displacement and force, they are in the same direction. But if the force is obliquely applied, like in this case, then work is not simply going to be force into displacement. Work is going to be f cos theta, the component of the force which is in the direction of displacement into displacement. That's how we define work. And this work is going to be studied in full-fledged chapter which is called work energy power. So I'm not bringing home the concept of work now. I'm trying to tell you what is the idea of defining scalar or dot product. Now you see from here, work is f into d into cos theta, and this could be written as f vector dot d vector, because a vector dot b vector is ab cos theta. That's how we have defined dot product. So f dot d is fd cos theta. So this is another example where simply the simple arithmetic kind of multiplication of two quantity will not give the required quantity. Work is not simply force into displacement. Work is dot product of force and displacement. So more of discussion we'll have in the chapter of work, but for now I just wanted to show you that what is the requirement of defining such a quantity. I hope the context is set, and now from here what you have to take away is simply this: a vector dot b vector is equal to ab cos theta. That is what you have to know initially, nothing else. Rest of the thing I was just talking and discussing about just to help you understand as to why we are studying this. It's going to help later. So a vector dot b vector is equal to ab cos theta. That is the dot product of a and b. Dot product is written as a vector dot b vector. It is read as a vector dot b vector, and that is ab cos theta. This is the definition of dot product. P vector dot q vector will be pq cos theta. P and q are the magnitudes of p vector and q vector respectively, and theta is the angle between the vector. Okay. Now certain observations we'll have based upon the dot product or scalar product. One is, of course, it's a scalar product. It doesn't have any direction appended. The left hand side you are dealing with vectors, but right hand side is a pure number. There's no direction there. So this is scalar product of two vectors, and also called as dot product. Apart from that, you would see that a vector dot b vector would be same as b vector dot a vector, because a vector dot b vector is a into b cos theta, theta being angle between a and b, and this would be b into a cos theta, theta being the angle between a and b. Theta would be the same in both cases, and this is simple multiplication. A b cos theta or b a cos theta, that would be the same. So a vector dot b vector is same as b vector dot a vector. This is called commutative property, which scalar product or vector or dot product satisfies. Now this you will have to think about. A vector dot B vector plus C vector would be the same as A vector dot B vector plus B vector dot C vector. Now you can have a feeling of this, you can analytically think, but I'm not giving you any proof. You can cite instances and you can cross check this. You can take three vectors in any orientation. For example, you can take three vectors like this and try and do dot product. You can consider one to be A, B and see whether this property is being verified or not. So I'm not giving any formal proof of this because this is very intuitive and natural. You can verify in certain instances. Do that, please. Because I've told you before, it's about more of your own thinking and how much you intrigue yourself. That's going to count, and that would be actually the difference between you or somebody else who performs better than you. Because stuffs are there in the book, everyone knows. You can buy books and books, but it is actually, what matters more is how much time you spend with yourself thinking about things, how much things you figure it out on your own. That is actually going to make a difference.